Hello. In this video, I will demonstrate how to use the Microsoft Excel solver to solve a linear programming problem and then conduct sensitivity analysis. So let's get started. Before I start defining the problem, I want to make sure that you have actually installed the Excel solver. So to do that, you go to File, and you go to Options, you go to Add-ins, click Go To, and then check mark the solver add-in to make sure that you actually do have the Excel solver installed. Okay, now we define our problem. The Nutmix Inc. produces three types of a specialty trail mix for export. They are standard, deluxe, and premium. Each bag of the trail mix weighs about 3 pounds and it's made of combining 2 or more of 5 ingredients as follows. The standard bag is made of half a pound of raisins, 1 pound of peanuts, 1 1/4 pound of sunflower seeds, and 1/4 pound of cashews. The deluxe bag is made of half a pound of raisins, 0.5 pounds of peanuts, 1/4 pound of dried fruits, 1 pound of sunflower seeds, and 3/4 pounds of cashews. The premium bag is made of half a pound of peanuts, half a pound of dried fruits, 3/4 pound of sunflower seeds, and 1 1/4 pound of cashews. The daily availability of these 5 ingredients are as follows. We have 20 pound of raisins, 25 pounds of peanuts, 15 pounds of dried fruits, I'll just call them fruits, 30 pounds of sunflower seeds, I'll just call them seeds, and 10 pounds of cashews. And the contribution to profit per each 3-pound bag of the 3 products are as follows. The standard is 75 cents, deluxe is $1.50, and the premium is $2. I am now going to formulate this problem as a linear programming problem with the 3 decision variables, standard, deluxe, and premium, and the 5 resources or constraints. So let's take a look at our LP model. This is the worksheet that I'm going to be using to enter my model. So first, we define our 3 decision variables, standard, deluxe, and premium. And they are number of bags of standard mix to produce, of course that's the 3-pound bag, number of bags of deluxe mix to produce, number of bags of premium mix to produce. You could alternatively call the decision variables x1, x2, x3, or x, y, and z. It really doesn't make any difference. Now we will form our constraint coefficients and coefficients for objective function. Here's my variables, standard, deluxe, and premium, and these are my resources, or we call them materials, raisins, peanuts, fruit, seed, and cashews. And as you recall, a bag of a standard mix uses 0.5 pounds of raisins, 1 pound of peanuts, no fruits, 1 1/4 pound of seeds, and 1/4 pound of cashews, and the contribution to profit from standard is 75 cents. Similarly, the deluxe bag uses half a pound of raisins, half a pound of peanuts, 1/4 pound of fruit, 1 pound of seeds, 3/4 of cashews, pound of cashews, and the contribution to profit is $1.50. For premium, does not use any raisin, half a pound of peanuts, half a pound of fruits, 3/4 pound of seeds, and 1 1/4 pound of cashews, and the contribution to profit is $2. And my relationship for the 5 constraints are less than or equal to, and these are my availabilities, 20 pounds of raisins, 25 pounds of peanuts, 15 pounds of fruit, 30 pounds of seeds, and 10 pounds of cashews. In this column, I am going to be entering the amount of resources or each ingredient that is going to be used by the mixture. But first, I need to define the 3 cells for the 3 decision variables: standard, deluxe, and premium, their values. And I'm going to use these 3 cells for that purpose. And I will place my total profit in this cell. So first of all, in order to define, I'll start with defining the total profit. In this case, the total profit is going to be equal to the sum product of the values of my decision variables, which will be entered eventually, and I'll make that absolute cell reference just in case I have to copy that, multiplied to the objective function coefficients. So in order to demonstrate how this formula works, notice if I put a 1 here, I get 75 cents. I put a 1 here, I get 225, and put a 1 here, I get 425. These values will be replaced with the optimal values for the decision variables eventually. I'm going to leave them alone for now. Now I'm going to define the amount of ingredient used by the combination of the 3 decision variables, and this is going to be equal to the sum product of the 3 decision variable, the values, and I'll make sure they are absolute cell reference so that I can later copy them to the other row, multiply to the coefficients for the first constraint, which is raisin. Okay, you can see that 1 multiplied to 0.5 plus 1 multiplied to 0.5 is 1. Because I used the absolute cell reference, I can now copy this formula all the way down, and that gives me the definition, amount of ingredient used of the second ingredient, third ingredient, fourth ingredient. We are now actually ready to enter our data into the solver and solve the problem. I'm going to reduce the size of the spreadsheet a little bit so that I can have enough room to work. Click on data and then solver, and let me park it here. First thing, I have to enter my objective function value. That objective function value is right here. Okay, I want to maximize, so I leave this alone. Next, I want to define my decision variables, so I highlight these. Okay, now I have to add the constraints. There are 2 ways to add the constraints. You can add them one constraint at a time, and I'll show you that first. So just type add, and you put used in here. The relationship is less than or equal to, and the total available is equal to 20. So we can just add that, and you go through this one constraint at a time. Alternatively, let me remove these first. Alternatively, you can just go ahead and click add and then highlight this cell, these cells. Because the relationship are all less than or equal to, I can do it in one shot. If these constraints had different relationships, I would have to add the constraints one at a time. And then of course lastly, my total available, or the constraint. And I click add and then say cancel. So here's my all 5 constraints entered. We have non-negative decision variables, so we leave this check mark. We want to solve it using simplex LP. Be careful because the default is the non-linear one, but we want to use simplex LP. And you can choose a variety of different options such as show iterations, etc., etc. I'm just going to bypass those and go ahead and say solve. When solver solves the problem, you can see that the decision variable values changed. I want to look at the sensitivity analysis, so before I accept the solution, I highlight sensitivity and say OK. The sensitivity report will be placed on a separate sheet. Okay, so this is my optimum solution. The solution is to produce 18.18 bags of standard, 7.27 bags of deluxe, no premium, for a total profit of $24.55. We can now look at the sensitivity report, which is placed right here. The sensitivity report consists of two distinct sections: the variable sections and the constraint section. On the variable side, first you have the three decision variables. At optimality, the values are 18.18 for standard, 7.27 for deluxe, and 0 for premium. The reduced cost show the change in the objective function value as a result of 1 unit change in the value of that decision variable. Obviously, we are producing both standard and deluxe, so they have 0 reduced cost. However, we are not producing premium, and if we were to produce 1 more unit of premium, our total objective function would be reduced by 25 cents. These are the original objective function coefficients. These are the allowable increases and the allowable decreases. By the way, 1 times e plus 30, which is 1 times 10 to the power of 30, is infinity inside of Excel solver. So this means that for this optimum solution combination to remain optimum, the objective function coefficient of standard can be increased by 25 cents, and that won't change the optimality, or it can be decreased by 25 cents, and that won't change the optimality. Similarly, for the deluxe mix, you can increase the objective function coefficient from 1.5 to 2.25, and the solution, the optimum combination, remains the same. Or if you reduce it by 0.125, that would change the optimum solution. Now we look at the constraints. The 5 constraints have to do with the resources: raisins, peanut, fruit, sunflower seeds, and cashews. The final values for these resources are 12, 21, 1.8, and 30 and 10. Let's look at the original right-hand sides. We had 20 pounds of raisin, we had 25 pounds of peanut, etc., etc. Notice that producing 18.18 bags of standard and 7.27 bags of deluxe will use actually 30 pounds of the seed, sunflower seed, and will use 10 pounds of cashews. And as a result, it uses up all of the resources available. Slacks will be 0. Let's look at the shadow prices. Shadow price is the marginal value of a resource. That is, if I had 1 extra unit of that resource, in this case raisin, let's say 1 extra pound of raisin, how many dollars that would increase, in this case, the objective function value. In this case, it's 0. Why is that? Because we are not using up all of our raisins. We are only using 12.7 pounds out of 20 pounds. Therefore, the shadow price is 0. The allowable increase is infinity. If you had more of that, still wouldn't change anything. The allowable decrease is 7.27, which is the difference between 20, and 12.72. If you reduce the available raisins below 12.72 or reduce it by more than 7.2, that would change the optimum solution. The interpretation for peanuts and fruits are pretty much the same. The shadow prices are 0 because we are not using up all of our peanuts, we are not using up all of our fruits. However, the shadow prices for seeds and cashews are positive. What this means is that if I had an extra pound of sunflower seeds, I could increase my objective function value by 27 cents. That's what I said. It's the shadow price is the marginal worth or value of a resource. If I had 1 extra pound of cashews, I could raise my objective function value by $1.63. The allowable increases and the allowable decreases are stated here in this section. And this is how we use the Microsoft Excel solver to solve a linear programming problem and then obtain sensitivity analysis report and try to do interpretation of the sensitivity results.